Hello students, welcome back to DHS Chemistry. Today we're going to be talking about stoichiometry. So get out those pencils and paper. Heyo!
Yes! Yes, Sam! Yes, Jenny! Exactly. That's what I've been saying, and now you see it. That chemistry is cooler than chat snap. Am I right? Ha ha! That's right, buddy! Eat my dust! No one messes with the mayor of Cheddar-Town. I prefer Cheetos right now, but that's okay. Come on now. I'm just semi-embarrassed. Welcome back. It's nice to see you again, but remember, video games are for only when homework's done. Of course. Anyways, you've all proven yourselves to be most valuable cheddars. So let's go to the DHS virtual laboratory.
Password.
I miss Healy Fridays. Yes, we're back. Ha! Jerry, Cindy, keep up the good work. Beatrice? Hey, just because I beat you in Mario Kart last night doesn't mean you give me the silent treatment. Ha! No one likes a sore loser. People still play Nintendo 64, right? Of course. Anyways, so what we're going to be doing today in DHS's virtual laboratory is talking about stoichiometry. What is stoichiometry?
Well, stoichiometry is the relationship between the relative quantities of substances in a chemical reaction. So looking here, this is an example of a chemical reaction. More specifically, a combustion chemical reaction. So, I like to compare stoichiometry to baking. Booyah, look at that guy there. For example, here's a recipe for 20 cookies. See the numbers next to the ingredients, like 2 tablespoons of brown sugar and 1 large egg? Well, these numbers can be compared to the numbers in a balanced chemical reaction. So, looking at Grandma Bird's Nest recipe, you need 2 tablespoons of brown sugar and 1 large egg to make 20 scrumptious cookies. But looking at this chemical reaction, which we can think of as a recipe, instead of talking about sugar and eggs, we're now talking about C5H12, aka pentane, reacting with oxygen gas to produce carbon dioxide and water. But the numbers we're looking at are the coefficients, or balanced numbers. And to make the perfect recipe here, we need 1 mole of pentane to react with 8 moles of oxygen gas to produce 5 moles of carbon dioxide and 6 moles of water. Delicious. So, in stoichiometry, we always use balanced chemical equations. And in this bad boy, it's the old 1856. So today, we're going to review 3 types of stoichiometric problems. The first type, mole to mole, is going to require 1 step. We're going to do some mole to gram. Those are going to require 2 steps. And then gram to gram, which require 3 steps.
Alright, so mole to mole stoichiometric problems. And before we even read the question, looking at our chemical reaction, we can see it's a skeleton equation. It is not balanced yet. And remember, we need to have the same amount on our reactant side to our product side. The law of conservation of mass, right? So we have 1 iron over here, but 2 here. We have 3 oxygens over here, but 2 over here. Remember, this is separating our reactants to our products. So we got to balance this bad boy. Let's do that together. Well, we have 2 irons here, 1 here. So we think to put a 2 here, but we have even number of oxygens here and an odd number here. So 2 and 3, the smallest number that goes into is 6. So if we do put a 2 here, Well, 2 times 3 makes 6 oxygens. So to get 6 oxygens over here, we put a 3, because 3 times 2 is 6. Oxygens are balanced, sweet. Irons, well, 2 times 2 is 4, so there's 4 irons on our product side. So let's just put a bad boy 4 here. 4 irons, so it's balanced. I like to call this the old 4-3-2. Booyah! All right, so once we have this bad boy balanced, the old 4-3-2, right? This is just like a recipe. Instead of cookies, we are making iron 3 oxide. So if we had 4 moles of iron, reacted that with 3 moles of oxygen gas, well, we're going to make 2 moles of Fe2O3. So sweet, that's exciting, I know. Now, how do we do these problems? Well, first, probably want to read it, right? Yes. How many moles of O2 are needed to produce 5.1 moles of Fe2O3? So how to start these, and to start all these problems, I think it's best to get in a rhythm. And I think the easiest way is to circle what we're looking for, and our hint is how many. So how many moles of O2? That's what we want, moles of O2. And because we're going to be using this recipe, this chemical equation, we're going to point to O2's coefficient, or balance number. All right, here's O2, and it's 3. So how many moles of O2 are needed to produce 5.1 moles of Fe2O3? So we'll underline the number given, and that's the number we're going to start with. And again, we're going to point to Fe2O3's coefficient, its balance number. So yes, this is the old 4-3-2, but right now we're really only caring about these ratios, 3 and 2, because we're talking about O2, and we want to find out about Fe2O3. All right, so once we have it set up, remember the number we underlined is the number we're starting with. It's given 5.1 moles, so it's unit and what we're talking about, Fe2O3. Remember, that's just always over 1. Sweet, that's our first setup right there. So this is a mole-to-mole problem because the number we're starting with is in moles, right? 5.1 moles of Fe2O3. And we want to end in moles. How many moles of O2? So we're going from moles, and then we're going to end in moles. But the thing is, we're starting in Fe2O3, but we want to talk about O2. So if we have moles Fe2O3, we know we have to have that down here, moles Fe2O3, right? Unit cancellation. Whatever unit's here, it's got to be down here. So how many moles of Fe2O3? Well, that's what our arrow pointing was for. We look at our balanced chemical equation, Fe2O3, and there's 2 moles of them. Sweet. But remember, we want to get to how many moles of O2. So that's on top, moles O2. How many moles of O2? Well, consult the chemical equation, 3 moles of O2. So 3 goes on top. Moles Fe2O3 cancel out with moles Fe2O3, and we're left in moles of O2, which is what we want to know, how many moles of O2. So we're ready to solve. And this fraction right here, or this conversion, this mole-to-mole ratio, is called the stoichiometric step. And remember, what that's for is just a old switcheroony. It's to get us out of what we're talking about. We were in moles of Fe2O3, and we're just switching into moles of what we want to talk about, which is O2. So this little stoich step is super important for these next coming problems.
Stoich step is just used to switch to what we want to talk about in the chemical reaction. Trust me, you'll be talking about the stoich step in college when you're wearing Birkenstocks with socks on, playing frizz on the college campus.
All right, so yeah, we're ready to solve. And remember, how we plug this into our calculator is we multiply all the top numbers. So that's 5.1 times 3. So 5.1 times 3. Enter gets us 15.3. And we're going to divide that by all the bottom numbers. So we'll go divided by. So our answer divided by. Remember, when we have numbers on the bottom, we need to use parentheses. So parentheses 1 times 2. So 1 times 2, close the parentheses, enter. 7.65. Sweet. So, since our starting number started with 2 significant digits, we can round our 7.65 to 2 significant digits, which would be 7.7. So, our answer is 7.7 moles of O2. Box that bad boy up. Oh, God. That's, this is low budget here. Give me a break, guys. All right, so if we're producing 5.1 moles of Fe2O3, well, we're going to need 7.7 moles of O2. Trust me, that will be useful for you in about 3.2 years. You're welcome. So, moldogram problems. Now, looking at this problem, we're using the same balanced chemical equation, the old 4-3-2. Remember, it's just like a recipe, where if we had 4 moles of iron to react with 3 moles of oxygen gas, we would produce 2 moles of iron 3 oxide. So, let's read the old question. How many grams, of iron are needed to react with 0.65 moles of O2? So we know it's a mole to gram problem because the number given is in moles and it's asking us how many grams. Moles to grams. Booyah. So remember, the setup for these problems never changes. So it's asking us how many grams of iron. So we circle what we're looking for and our hint is how many. How many grams of iron, and we're going to point to its coefficient, its balance number, which is 4. Iron's coefficient is 4. So are needed to react with 0.65 moles of O2. Underline the number given, which is 0.65 moles of O2. We're talking about O2, so we're going to point to its coefficient, its balance number. So yes, this is the old 4-3-2, but in this question, all we care about is the old 4-3. All right, so start with the number given, the number we underlined, 0.65 moles O2 over 1, right? And how we do these. If we are in moles of O2, well, yes, we need to be in moles O2 down here. Cancel out our units. How many moles of O2? Consult our equation. Well, it's 3 moles of O2, the arrow we pointed to. And this is the Stoich step, right? It's just switching of what we're talking about. We're in moles of O2, but we want to talk about iron. So moles of iron, we pointed to that 4 up there. There's 4 moles of iron. So remember, this is our Stoich step. It's just used to switch what we're talking about. We were talking about O2, now we want to talk about iron. Sweet. We would be done right now if it asked us how many moles of iron, but it's not. It's asking us how many grams, so we got to keep going. So moles of iron, got to have moles of iron down here. And what do we want to end with? How many grams of iron? So grams of iron. And where are we going to find grams? Of course. Ha ha. You think I'm kidding now? No. Grams of iron, well, molar mass of iron is 55.85 grams. All right, 55.85 grams of iron is equal to 1 mole of iron, as we know. So now we are ready to solve. All right, so remember, it's just timesing or multiplying all of our top numbers, which is 0.65 times 4 times 55.85. Enter 145.21 divided by, so our answer dividing by our bottom numbers, have to have parentheses. So parentheses 1 times 3 times 1, close parentheses, enter. 48.403333333. You get the point. Well, the number we started with was 0.65 moles of O2, two significant digits. So let's give our answer in two significant digits. So our answer is just going to be 48. So it is 48 grams of iron. Bam.
No, I'm not afraid to do the Lord's work. You say vengeance is his, but I'ma do it first. I'm gonna handle my business in the name of the law.
All right, so to take us through gram-to-gram stoichiometric problems, we're going to call in DHS big leaguer, Mrs. Tidwell.
Hey guys, this video is just a good reference for you. It's me modeling several stoichiometry problems step by step, just so that you have a pattern to follow if you need it. All right, notice first of all that I've written some equivalences here that are from our chapter on the mole, and these equivalences will be used to build conversion factors in stoichiometry problems. I'm hoping that you have a hard copy of this paper or the ability to download it from your computer wherever your teacher posts work for you. If neither of those are possible for you, if you can't download it and print it and have a hard copy, then I suggest that you just write the problems on notebook paper, and you can certainly pause the video as we go along to give yourself time to copy and then start the video again so you can fill in the problem. All right, so in each problem, you'll have a balance equation, which is absolutely vital for stoichiometry problems. And then as you read the problem, the first thing I want you to do is to look for the question word and circle the quantity that you're being asked to find. So I'm reading, if you react 235 grams of silver nitrate, how many grams of zinc will you need? Okay, here's my clue. How many? That's my question word. And I'm going to circle grams of zinc. That is what I'm trying to find. And then I'm also going to take my pen and I'm going to go to the balanced equation and find this substance, zinc, and I'm going to arrow it. I'm arrowing the implied 1 that's in front of zinc. All right, and then I'm going to switch pens and I'm going to read the problem again and underline the given quantity. If you react 235 grams of silver nitrate, okay, there is the given number, unit, and substance. And then I'm going to go up to my balanced equation and find that substance, silver nitrate, here it is, and I'm going to arrow that in the balanced equation. These two pieces give me the mole-to-mole ratio for these two substances, and that's how I will build my stoichiometry step. All right, now I've marked up my problem. The next thing is to go to this given quantity and write it down, number, unit, and the stuff, the identifier, the substance. Taking that given amount and I'm putting it over 1. That's always our first step. Second step is to look at this unit, grams of silver nitrate. If that unit is not moles, and this one isn't, this one is grams, then my very next step is to change grams of silver nitrate into moles of silver nitrate. Okay, to do that, I need to make use of the periodic table because I have an equivalence that tells me 1 mole of substance is equal to its molar mass from the periodic table. Right, so periodic table. So right here. All right, so I am going to build a fraction here that says 1 mole of silver nitrate, and then I'm going to use my periodic table to add up the molar mass. Let me come over here to the side. Silver nitrate has silver, nitrogen, and oxygen. In this formula, there is 1 silver. Silver has an atomic weight of 107.87. So one of those weighs 107.87. Now I have nitrogen. There is 1 of those in my formula, and nitrogen's atomic weight, 14.01. And lastly is oxygen, and in this formula there are 3 oxygens, and oxygen's atomic weight is 16.00. 3 of those weigh 48.00. Now I grab a calculator and I add up those pieces. 107.87 plus 14.01 plus 48.00, and 169.88 is the molar mass. So 1 mole of silver nitrate weighs 169.88 grams of silver nitrate. All right. Grams of silver nitrate divide out. Okay, now I have in my numerator moles of silver nitrate. Once I've worked my way to moles of the substance, I am ready to do the stoichiometry step. So I look up here at my 2 quantities that I've marked with an arrow, and these 2 quantities tell me that in this reaction, 2 moles of silver nitrate are equivalent to 1 mole of zinc. This step that I just constructed is called the stoichiometry step or the stoic step. Notice that it's the switching step. It takes you from this substance, silver nitrate, that we started with, and now it's switching to the other substance, zinc. All right, I am looking in this problem for grams of zinc, so I can't stop here. I have to go another step. And again, I know from these equivalences that 1 mole of a substance has a molar mass determined from the periodic table. 1 mole of zinc has a mass of 65.38. grams of zinc. Moles of zinc divide out. Now I have worked my way to grams of zinc, which is exactly what I'm looking for. So now it's time to grab my calculator, and the way we do these problems is we work straight across the numerator, just simply typing in 235 times 1 times 1 times 65.38, and then you hit equal. Okay, this is my numerator, and now I'm going to divide by, and when I go to the denominator, I always wrap the whole thing in parentheses. So I type parentheses, and then I have on my denominator 1 times 169.88 times 2 times 1. When I get all the way across the denominator, I close the parentheses, and then I hit equal. And my answer, 45.2. Notice I rounded it to 3 sig digs because my starting number. had 3 sig figs. So 45.2 is the number part of the answer, gram is the unit part of the answer, and zinc is the substance part of the answer. Put it in a box, and we're done.
No, I'm not afraid to do the Lord's work. You say vengeance is his, but I'ma do it first. I'm gonna handle my business in the name of the Lord. Now if he made you cry, oh, I gotta know.
Congratulations on making it this far. It's a high probability that I'm talking to myself right now. I mean, right? I don't know. Whoa. Okay, anyways, I hope you learned something today about stoichiometry. What do you think about a lab assistant? Yes, very astute observation. That's why we keep them around. Anyways, remember, stay safe out there and keep your periodic tables on you at all time. Hey, until next time.